Yeah, so just as we have a few people missing today, I'll record this, although there's nothing particularly new within what I'm just going to talk about today. And then we'll have some questions for you to work through, and people can check in with me, answers, ways to solve them. Yeah, so I think it's all gone pretty well. So just to start, as with a summary of everything we've gone through. So this is very, very brief, but I was thinking about it recently, and the relationship between all of these concepts, forces, energy, power, work, they can be quite difficult things to explain. And I mean, I know we all find moving boxes across floors fascinating, and physics has really developed this area substantially in the world, but there is something far more important which I think illustrates this point, and that is rugby. So I have picked at complete random, I assure you, a Scarlets player, Ken Owens, in this case featuring for Wales. And so before we start, do we have any Ospreys fans here? Excellent. I was gonna suggest that their marks would be capped at sort of 50%, because I'm not in a good mood after last weekend. But generally speaking, that's great to hear. So anyway, if we look at Newtonian mechanics in terms of rugby, we have a player. So this is Ken Owens. When he's not moving at a state of rest, it requires some force to get him to start moving. And so this is then F equals ma, Newton's second law. Because it is proportional to mass, then in the nicest of possible ways, Ken Owens is quite a big man. We will require a fair bit of force to get him to start moving. By the same token, we also need a force to get him to stop moving once he has started. And again, because he does have a decent mass on him, this force is quite large. And so this is then the concept of inertia. But then let's say Ken is 10 meters from the try line. Yep, no problems, Ronnie. We just started. And so then we take Ken, and he's 10 meters from the try line. So for him to get to the try line to score a try for Wales, hopefully beating England with the final play of the game, but I'll put that up for debate as to where people's loyalty lie. We need to actually do work to achieve this. And so work done is then equal to force multiplied by displacement, which is then delta x. We've already seen force is equal to mass times acceleration. And so then we can say, we can start putting some real numbers into this, and in some ways they're approximations. So Ken Owens actually weighs 110 kilograms. And let's say he needs to get to an acceleration of 0.1 meters per second squared. And so from this, we can then say the work we need to do for Ken to move this 10 meters is equal to F delta x, so is equal to mass times acceleration, 110 multiplied by 0.1 multiplied by the displacement, which is 10. So this would then require 110 joules of work, of energy, to achieve this. And this then brings us to this concept of how work and energy are related. So this is in some ways, I would say, possibly the trickiest part of this thought process, which is we've already defined the work needed as 110 joules. And if you remember, I brought up the concept of energy being the capacity to do work. So within my rugby analogy, if we give Ken the option of drinking one of two drinks, be it just water, which contains 10 joules of energy, or an energy drink, which contains 500 joules of energy, you can hopefully see that the water wouldn't contain enough energy to actually supply the required amount of work to get him this 10 meters. So he'd only be able to move 1 meter before then running out of juice. And so that hopefully illustrates the difference between the two. Finally, power. And so power comes in how quickly we're able to do work. So within a sport such as rugby, being able to move distances quickly is definitely an advantage, particularly if you are quite a sizable unit, as Ken is. And so if he's required to do this in 3 seconds to avoid being tackled, for example, this is then where the power of the unit comes in. So we go back to power being equal to work done divided by time. We've already calculated the work done as 110 joules. And we have now introduced the concept we need to do this within 3 seconds. When we divide 110 by 3, this is then equal to 36.7 watts. And so for all of this to happen, Ken's legs need to supply in total 36.7 watts of power. And just as the final observation for this aspect is, we can go back and look at the Pontypool front row from the 70s. And let's say these guys weigh the same as Ken. However, because this was in the amateur era, they didn't have the same training methods. They probably didn't take things like anabolic steroids either, but that's hopefully off the record. They don't actually have the same power in their legs. And so in this case, just for example, say they only have 20 watts of power compared to Ken's mighty 36.7. And so now we can look at power being equal to work done divided by time, rearrange it, and we can work out that for exactly the same activity, so the same amount of work done, 110 joules, divided by their power of 20, this would then take each of these guys 5.5 seconds to do. So hopefully that brings together these concepts. And even though there won't be any questions on this next aspect, but I think it's important to at least be introduced to it, just for the sake of completeness of Newtonian mechanics. And that is to say that not all things move in straight lines. So even though we have encountered many boxes moving horizontally or vertically and so on, of course, this isn't very realistic. And one of the exceptions is things moving in a circle around a fixed point. So this can be demonstrated by planets orbiting the sun, the moon orbiting the Earth, electrons around the nucleus in the particle theory of electrons, and so on and so forth. And the important thing to be aware of is that even though you have something orbiting at a fixed speed, there is actually a constant change in velocity. So velocity has both magnitude and direction. And if you think, this angle is always changing. And so because there's a constant change in velocity, there must be an acceleration. And if this has mass and there's an acceleration, there must be a force somewhere. Well, a pair of forces, in fact. And so whilst I won't go into the maths in this in too much detail, we can solve this so we can have both an initial velocity VA and a final velocity VB with the angle between them of theta. This enables us to calculate a change in these velocities, so delta V. And working through the maths of this, we can then arrive at an expression for the centripetal acceleration, or A with a lowercase, subscript c. And so this is then equal to the square of the velocity, so the orbiting velocity, divided by the radius. And I will repeat, we're not going to do questions on this, but I think it is very useful to be aware that this is also apparent from Newtonian mechanics. And so, as I said, any deviation in travel from a straight line, Newton described as being the result of a net external force. And this is no different for circular motion. And in circular motion, the force is actually acting from the center of the mass to the center of the orbit. This is provided by several varieties of the same equation, which again, don't worry about or bother yourself with, but for the sake of completeness, I've just put the